Date 2019, mechanical metallurgy. During the low strain rates, less than 0.1 second per second, the deformation of metal at room temperature. The one that deforms by twinning mode. Generally, twinning mode deformation happens mostly in HCP metals. And the slip deformation happens generally in FCC and BCC. So out of this all, uh, magnesium has HCP structure. And now, in tensile creep test of a metal, never a herring mechanism is favored over cobalt creep. See, the condition for, if you see Navarro, the creep rate is inversely proportional to square of the grain size. In cobalt, is inversely proportional to cube of the grain size. So, cobalt is preferred at lower temperatures and lower grain size, and Navarro is generally for coarse grain size and at high temperatures. So Navarro is favored at larger grain size and higher temperatures. The beach marks are commonly observed on the fracture surface after. Generally, the if you'll see the samples of fatigue, you will observe these kind of striations or beach marks. This is observed mostly in fatigue test on the fracture surfaces. The length of internal crack in two samples of same glass is measured to be C1 equal to 0.5 mm and C2 is equal to, okay, the ratio of sigma 1 by sigma 2 of the fracture stress. Okay. The fracture strength of the sample is given by sigma is equal to root over 2e gamma by pi c. So sigma 1 by sigma 2 equal to root over C2 by C1, which is equal to root over C2 is given as 2 and this is 0.5. So root over 4, it is 2. So sigma 1 by sigma 2 is nearly 2. An aluminum single crystal is loaded in tension along 1 bar 0 axis. Among the following slip systems, the one will be activated first is. If you see, the one will be activated, you need to calculate cos phi and cos lambda. Apply Schmidt rule here. Schmidt rules here. So it is uh, 1 bar 0 into 1 1 bar by root over 2 into root over 3 into 1 bar 0 0 1 bar 1 by root 2 into root 2 for A. For B, the same 1 bar 1 into 1 bar 0 into 1 bar into 0 1 1 divided by root 2 into root 2 by root 3 into root 2. Here also it is 1 bar 0. You do the same way. D is also same way. So here if you see it is this is not equal to 0 and this is not equal to 0 and here it is 1 bar 0, this is 0 and here it is 0. We will multiply with this and 1 bar this is also 0. So the one will be activated first which does not have tau CRSS as 0. This is the correct Mohr circle construction for the stress state is given by here we know sigma y is given as 30 and tau xy is 20 and sigma x is equal to minus 10. The first of all we'll try to find out the center of Mohr circle. The center of Mohr circle is given by these ends by 2 and these one by 2. So it is sigma x plus sigma y by 2 comma 0. Okay. If you'll also find out that all the center is almost lying at on the x-axis itself. So here it is 30 minus 10 by 2 comma 0 is 20 by 2, which is 10 comma 0. And among these, 10 comma 0 is only in this. So the Mohr circle represents this one. The cold working The cold working of iron leads to increase in dislocation density from 10 power 10 to 10 power 15 per meter square. The associated stored energy, you need to find the associated stored energy in megajoules per meter cube. The shear modulus is given as 82 GP and Berger vector is given as A by 2. Okay. You know, the associated total stored energy is half GB square into dislocation density. It is generally per meter and now it is per meter cube. So now half into 82 into 10 power 9 into Berger vector is root 3 A naught by 2. So it is root 3 by 2 into 2856 into 10 power minus 9 whole square into it should be an average of the dislocation density. So the difference between them, how much to increase this dislocation from 10 power 10 to 10, what is the energy associated? So it is 10 power 15 minus 10 power 10. So nearly it is 10 power 15 only on an average. So if you'll calculate this, you'll be getting 2.5 megajoule per meter. The answer is 2.5. The material, which is made up of alternating layers of metal A and metal B, is loaded as shown below. If the volume percentage of B is 25%, the elastic modulus is given as. Here, the stress is applied in transverse direction. We know in transverse direction for composites, 1 by EC is equal to VF by EF plus EM by EM. So you need to find the elastic modulus of the material. So it is VF, the volume of the fiber. Here B is the fiber. So 0.25 by the EF is, so for B it is 100 plus 0.75 by 200. It is 160 GPa. The SN curve for steel is shown below. The stress ratio is sigma minimum by sigma max is equal to minus 0.8. The maximum stress the steel can withstand the infinite life is. Here, the maximum strength at which it can penetrate is sigma A is equal to 300. So, alternating stress is nothing but sigma max minus sigma min by 2. You have sigma min is equal to minus 0.8 of sigma max. So substitute this here. So sigma A is equal to sigma max plus zero point 0.8 sigma max by 2. So sigma max is equal to 300. Alternating stress maximum to have an infinite life, the alternating stress required is 300. So 300 into 2 by 1.8. This comes to 333.3. The true stress strain behavior of a metal is given by flow curve. Sigma is equal to 1750. Here it is given as true stress is this one and true strain is this one. The true stress at necking, at necking, the true strain is equal to strain hardening exponent. So at necking, E is equal to mu or N. So sigma is equal to 1750 into 0.37 power 0.37, which comes to 1211 ampere. That is 1211. Thank you.